Okay, let's get started. We got a bunch of housekeeping stuff to do today before we get back to lecture. So let's start by talking a little bit about the schedule. We are going to start in on lecture 4 today, which will be the first lecture in the second of 5 themes we're going to cover in this course, which is how to go about doing design that's specific to HCI. We spent a lot of time last week trying to scope out who, what, where, and when. Once you know all that, how do you turn that into the how, right? The technology that's going to support those people performing those activities in those contexts. So we're going to spend a bit of time today and Wednesday and Friday talking about design and specifically visual design. The week after that, I will not be here. I'm going to a conference in Edinburgh, Scotland. And the deal is that whenever I go to a conference and I'm not here, I bribe you by bringing you back food from wherever I'm going. What do you want from Scotland?
Haggis.
Haggis. I knew that was coming. All right, you asked for it. Haggis it is. I will. Okay, we'll make a list and then we'll go through it. I promise to bring back something that is delectable and appropriate for class. Okay, fair enough, fair enough. Okay, so that's the bribe. I will be gone all next week. Jeff Springer is a student who took this class a few years back. He's now the CEO of Zemo Software Corporation. They're developing educational games around robotics. So he is going to be using you all as guinea pigs. They're in the alpha testing phase. So you should be able on Monday to download a free version of Zemo, and Jeff will sort of walk you through that. And you're going to have to work for your alpha testing. He's going to want some feedback from you on what works and what doesn't work so well. On Friday, we'll be having another guest lecturer who will be one of the students from my lab who will be taking you through the beginning of the design process, specifically as it relates to HCI. So I won't be here the following week, but we're going to continue on with the deliverables as usual. If you get stuck, please make sure to go see the TA during his office hours. If the TA gets stuck, email me or possibly Skype me. We'll see how things go. All right, so far so good? Okay, so deliverable 2 is due tonight. There's been a number of questions about deliverable 2. Let me just try and give you a few hints that might help you out. Let's see. There was a little bit of confusion about step 9, which says remove the lines that print the 3D coordinates. Remember, you're just printing them as text to the screen, so you're just deleting that. You're not actually deleting the lines that you're drawing yet. There's a little bit of confusion about that. If you're having problems with deliverable 2, most of the time it has to do with indenting. As you know, in Python, the way you indent indicates which line belongs to which, in which context, which for loop, which if, which while, and so on. So as I mentioned, I think last week, matplotlib is not ideal for real-time 3D drawing, so it's a little bit awkward. In the innermost loop, you're adding a line, right? You're adding one line for each bone in the hand. When you finish that innermost loop of drawing all the lines, you come out of that innermost loop and draw, which displays all the lines to the screen. Then you delete all of the lines that you just drew. Make sense? That's the intuition. Most of the time it's adding the lines, the command to draw, or deleting the lines is not indented properly and you're deleting before you've drawn, or you're drawing after the addition of every single line, something like that. So if you're having problems with deliverable 2, check your indenting first. If that doesn't work, come see me or the TA. Any other questions about deliverable 2? Yes?
Just about pause, how Windows users are having to use pause
Okay.
to work.
Yes.
Is there enough? Because it's so, like...
Yes, it's not ideal.
Yeah.
Okay, it should be enough for now. There's no speed considerations. As I mentioned, you can switch over to, Pygame, which also does real-time drawing, but not in 3D. It does it in 2D, but it should be enough.
So we wouldn't have to use pause. It would be less choppy.
Famous last words. I believe so. I don't have a Windows machine, so I don't know. So if someone wants to try out this deliverable or the next one in Pygame, on a Mac or a PC, report back, and I'll put up an announcement on Blackboard, and if that's a better solution, you can migrate over to that. For, I think, pretty much everything we're going to do, speed is not really an issue. So if the pause is in there, that's not going to work against you. Yes?
For step 17, you talked about the strategy for adjusting the axes.
Yes.
So were you thinking that we'd have the same sort of dynamic adjustment, or just get those values and then hard?
Yes, that's a good question, right? It doesn't matter too much if you're doing it dynamically, right? So as the hand is moving, you're calculating what the minimum and maximum is now for 3 axes rather than 2. So if your video shows a little bit of dynamic adjustment of the axes, and then after a while you're not able to move the axes anymore, that's perfectly fine. If you do it dynamically, you hard code that and shoot a video just with the static axis, that's also perfectly fine. This is really just for your benefit because it might be slightly different on everybody's machine depending on lighting in your hand and so on.
So you'd be okay if we use like the interaction box class as opposed to doing the min and max, just because it gives you the maximum viewing range of the.
Yes, you can use whatever else you want, right? There's this underlying guiding principle in all these deliverables. If you come up with a different way of doing things, but you're still able to achieve what we want, is a hand moving about in a relatively large volume, it's fine with us, right? You're not handing in your code, you're just demonstrating to us that you're able to achieve the functionality that's described in the deliverables. Sound good? Okay, that's deliverable 2. Now we're going to talk about deliverable 3, which is due next Monday at 11:59. I won't sugarcoat this. Deliverable 3 is a monster. This is the longest one, so do not leave this till the night before. Okay, here we go. So I'm going to walk you through deliverable 4. It's not difficult. There's just lots of additional pieces that we're adding in deliverable 3. And I'm going to just very briefly go over all the major pieces of deliverable 3 now. Obviously, read it in detail at your own leisure. It weighs in at 12 pages and 45 steps. So again, get started as soon as possible. All right? Okay, so what are you doing in deliverable 3? I've tried to summarize this with the figures at the top. So in deliverable 1 and 2, you're establishing this basic feedback loop. Somebody waves their hand over the leap motion device. The hand information is captured by leap motion. That information is passed off to your Python program, which is capturing it from the leap SDK. You're then passing that off to matplotlib, which is drawing it back to the screen seen by the user, right? As I mentioned, everything we're going to do in the rest of this course is complicating this basic feedback loop. Here's that same feedback loop. So this is what you should have at the end of deliverable 3. You have the same feedback loop going from the user to your Python code to drawing something in real time that's seen by the user. We are also now adding in saving and loading capabilities. So you're going to capture data from the user's hand and store that in a data file. And that data file can then be played back at a later point by a second Python program that you're going to be developing in deliverable 3 that will show what's been captured from the leap motion device. So at the end of deliverable 2, you're going to have 2 Python programs, one which does the real-time feedback loop, and the second one, which when it starts up, will look for data files and display a wireframe hand based on data stored in that data file. That's where we're going. Okay, so as I mentioned, we're going to be, let's see here, let me walk you through this. Let's do this in order. How are we actually going to do this? Well, we're going to do this in the following manner. We're going to create a visual analogy for the user to know that now in this program there is a record functionality. The way we're going to do that is show that there is a green hand. We're going to draw the hand in green, and green is going to be kind of our metaphor for play, so nothing's really happening while it's green. The user can then take their secondary hand, and move it into the field of view of the leap motion device. Remember, the leap motion device can detect whether there's 0, 1, or 2 hands over the leap motion device. The moment leap motion detects the second hand, it's not going to draw the second hand, it's just going to change the green hand to red, which means record. So we're going to introduce this metaphor that bringing the second hand into leap motion's field of view is implying record. When that happens, data is being sent to a data file. When you pull your secondary hand out of leap motion's field of view, the hand will turn from red to green, which means nothing's being recorded. So this is much simpler than having someone have to try and point to or click on a button that says record or play. You can just record by using your secondary hand. So the terminology in deliverable 3 is going to get a little bit confusing. We're going to talk about primary and secondary hand. So for me, I prefer to do ASL with my left hand, which is my primary hand, and my right hand is going to be my secondary hand, which is controlling play and record. For some of you, it's more comfortable to sign with your right hand, which will be your primary hand, and your secondary hand will be your left hand. So there'll be lots of mentions of lefts and rights and primary and secondary throughout deliverable 3. So is the intuition behind how we're going to record data clear? Okay. Again, there's more details there you can go and have a look at. The other thing we're going to introduce now in deliverable 3 on step 2 here is we're going to introduce object-oriented programming. So your program is going to become more complicated as we go. So you're going to switch things over into objects now so that it'll be easier, more modular. It'll be easier for you to modify things as we go. Who knows what a class or an object is? Who does not? Okay, a couple people. That's fine. You might want to go and read a little bit about object-oriented programming. For our purposes, we're going to introduce an object called deliverable. You can see on line 3J here, I create a variable called deliverable. So an object is a special kind of variable, if you like, which can store not just a value, but it can store an arbitrary number of other things. Among those other things are other variables or other objects, and they can also have associated with them functions. So you can see I'm creating an object here called deliverable, and that object, deliverable, has a function associated with it called run forever. Okay. So if we go down here to 4a, here's me defining my class called deliverable. And so far in step 4, it has 2 methods, which is a special name for functions associated with objects. One called run forever and one called run once, right? This should be pretty straightforward. Run forever, as the name implies, will just run forever. And every time through this infinite while loop, it will call another function called run once. You'll see on line G here this special notation in Python for object-oriented programming, which is self dot. So self refers to the class itself. So this particular class called deliverable has a function associated with it called run once. You can also have things like variables associated with it. So on line 5C, there's something called Selflines. So the class called deliverable has a bunch of variables called lines stored within it, right? So we're going to try and encapsulate or store all the data within just one object at the top called deliverable. This is going to make your life much easier as we go along. Is the basic intuition here pretty clear? Okay. You can, so I'm going to, in deliverable 3, you're going to modularize a bunch of things. So you're going to add a bunch of methods or functions to this class called handle bone, handle finger, handle hands, and so on. If you want to further modularize your code by adding new objects called bone, hand, position, 3D position, and so on, you're free to do so. Okay, any questions about that? Okay, let's keep going here. So on step 9 here, I talk a little bit more about the ASL language that we're going to be capturing from the leap motion device. Who here speaks ASL? Anyone? Okay, you can go and read a little bit about it. All of the letters and numbers from 0 to 9 in ASL are static gestures. So this is 0. You don't move. There are 2 letters, J, and I forget the one for Z, which are not static, they're moving. So we're going to try and keep things simple here. When your user records a gesture, they're just recording a static gesture. We're not going to record gesture over time. That would make things pretty complicated. So since 2 of the 26 characters are moving gestures, we're going to rule out characters for now, and we're just going to stick with the 10 ASL digits from 0 to 9. So at the end, when you build your ASL educational software, you're only going to be teaching your user how to sign the digits between 0 and 9. All right? So that's what you're capturing, is a single frame of gesture data, and we're going to use that in subsequent weeks when we introduce the machine learning part to recognize from that single frame, did the user successfully sign 0 or 1 or whatever they're supposed to gesture, or did they not? Okay. Okay, so how are we going to actually store all this information? We're going to use, you can see here at the top in step 14a here, we're going to introduce the third of 4 Python packages that you're going to use in this class. So we've already introduced matplotlib for visualization. We've introduced the Leap SDK, which 99% of you now have running on your machines. And now we're going to introduce the third one, which is NumPy. Who's worked with NumPy before? Some of you, not many of you. That's fine. So NumPy is short for numerical Python, and it allows you to manipulate large amounts of numbers relatively straightforwardly. From a practical point of view, this might be the most important thing you learn in this class, which is how to manipulate large amounts of numerical data in Python. Comes in handy in a lot of jobs these days. Okay, so I just want to, again, not describe all of how NumPy works, but give you an intuition for how NumPy works. NumPy basically allows you to do vector and matrix operations relatively straightforwardly. The nice thing about NumPy is we're not necessarily restricted to 2-dimensional matrices. We can create matrices of arbitrary dimension. And as you can see on step 15a, we're going to create a variable called gesture data, and that is made up of a NumPy matrix that's initially filled with all zeros. And that matrix has 3 dimensions. So these 3 numbers represent the length of each of the 3 dimensions in this matrix. So hopefully you remember from high school algebra, when you have a 2D matrix, you have a bunch of rows and a bunch of columns. In NumPy, we specify the number of rows first. So the 5 here tells us that in gesture data, we want to have a matrix that has 5 rows. The second number tells us that we want to have 4 columns. So far now we have a 5 by 4 matrix. And the third number represents that our matrix has a third dimension, which we're going to refer to as stacks. And it's going to have 6 stacks. 1, 2, 3, 4, 5, 6. So if it helps you, you can think of gesture data as storing 6 5 by 4 matrices and stacking them one on top of another. Okay, we're going to spend a fair bit of time talking about 3D matrices. So we good so far? Okay, given what you've learned about the Leap Motion SDK so far, what's the 5, the 4, and the 6 here? Why 5 rows?
5 fingers, 4 bones, 6 positions.
You got it, right? So we have 5 rows. So each row is going to store data about one of the 5 fingers. Each column, each of the 4 columns is going to store something about that bone in that finger. And the 6 stacks, if we pick an element in the matrix and drill through the 6 stacks, that will give us 6 numbers, which represents the starting 3D position and the ending 3D position of that bone. So far, so good? Okay, so basically one 3-dimensional matrix is going to store 1 frame of data from leap motion, right? And all the machine learning stuff that we're going to do in a few weeks is going to be manipulating these 3D matrices with the assumption that whenever it's passed a 3D matrix, that matrix contains all the information about the positions of the bones in the hand. Okay, I put together a figure for you here, which you'll probably use as reference for the rest of this course, so I just wanted to walk you through it. Let's zoom in a little bit here. Okay, so I think I've changed my mind a few times here. I keep forgetting. In leap motion, there are 4 bones for each of the 5 hands. There's a bit of a hack here because it turns out that your thumb is missing one of the 4 bones that your other 4 fingers have. So they create in leap motion a fictional bone called the thumb metacarpal. Doesn't exist, but they put that data into the frame, which makes our lives a lot easier. This fictional bone, the start and end position are the same. It has 0 length. And the position of that metacarpal is at the base of the proximal phalange of the thumb. Hopefully you don't need to worry about that, but just again, so we're all on the same page, 5 fingers, 4 bones. Okay, so here's my 3D matrix over here. You can see that this matrix contains 5 rows, 4 columns, and 6 stacks. Let's assume for the moment that I've stored all of the positions from one frame into this matrix, and I now want to manipulate that matrix and pull out information about this particular gesture. So in Numpy, you do that using colons and numbers. So let's take our gesture data here. I'll just put GD in front. This would actually say gesture data, open square bracket, end square bracket. So if I were to say print GD and put something in here, it will print out some numbers that are stored in this matrix. The colon on its own represents I want everything along that dimension. So if I put a colon in the first of the 3 slots here, that tells Numpy that I want data from all of the rows. If I put a colon in the second position, that tells Numpy that I want all of the data from all of the columns. And if I put a colon in the third position here, this says I want information from all of the stacks. So basically, if I said print GD colon, comma, colon, comma, colon, it would give me back a whole bunch of numbers. How many numbers would I get back? 120, right? 5 times 4 times 6. In figure A here, let's say I want just information from the thumb. As we now know, each of the 5 rows corresponds to the 5 fingers. We count, in Numpy, we count from the top down. So the first or the 0th column is at, the 0th row is at the top, and the 4th row is at the bottom. In leap motion, we count fingers starting from the thumb going towards the pinky. So the 0th finger is the thumb, and all the information about the 0th finger is stored in the 0th row, which is at the top. So if I were to change this and put in this, this would now not give me back 120 numbers. It would give me back how many numbers? 24, right? So 4 times all the 4 bones, and for each of the 4 bones, 6 numbers. So 4 times 6, 24, right? So the red rectangle here is capturing all of these numbers. So I've sliced off the top row of this matrix. Let's say I'm interested, furthermore, just in the distal phalange, information about just the distal phalange in the thumb. How do I need to modify my print statement here? Yep. So 0 in this position, right? We still want information about the thumb. What do we put here? A 0?
Three.
3, right. So leap motion counts from the thumb to the pinky, and then when we're counting bones, the 0th bone is the metacarpal index, proximal is 1, intermediate is 2, and distal is 3. So we're counting from the palm away to the tip. So if I were to call this statement, how many numbers would I get back? 6 numbers, which is the start and end position of the proximal, the distal phalange in the thumb. Okay, let's keep going. Let's say, like in deliverable 2, I want to throw even more information away and I just want the position of the tip of the thumb. How do I ask for just the 3rd, 4th, and 5th number in the 0th row and the 3rd column? So I can't use a colon because I don't want the whole thing. I just want the last 3 numbers. Any NumPy experts here know how this is done? You can put a number to the front of the colon and a number after, which will specify a range. So if I put in here 3:5, that means when I get this information back, at this point I have a vector of length 6. And this says I want now to return just the 3rd through the 5th element in that vector inclusive. So I don't want 0, 1, 2. I want 3, 4, and 5. So if I were to print this statement, I would get back a vector of just 3 numbers, which is the position of the distal phalange in the first finger of the hand. So far, so good? I think you're asked to do so in this deliverable, but if you aren't, I'd suggest you do these kinds of things. Just print out, sort of slice and dice your matrix and make sure you get back the number of numbers you're expecting, right? That you've grabbed the right information and you'll know your way around NumPy, or the NumPy data that's storing data from the leap motion device. Any questions about that? Okay, just to make sure we're building up our intuition about leap motion here, as I mentioned, for our purposes, we're going to restrict ourselves just to static gestures. If you want, in the final project, you can try and capture data over time. How would you extend NumPy here to capture, let's say, 10 frames of someone trying to sign the letter J? What change would you make?
Well, I mean, isn't each one of these matrices a single frame?
Exactly.
So you just have multiple matrices.
How would we do that? So we need to have multiple matrices. We need to have 10, 1 for each frame. How would you do that in NumPy? You were just going to say?
A list.
Exactly. So we could make a list. So we could go outside of NumPy and use standard Python data structures like lists and so on. But I want you to start thinking like a numerical programmer. So can we stay in Python and extend?
Could you add another dimension to it?
You got it, exactly. So let's go back a moment to where we actually defined the variable itself in line 15a here. So here we defined a 3-dimensional matrix. So we could define a 4-dimensional matrix, right? We could add a 4th number in here, which would basically give us a stack of 10 3D matrices. What's the 4th number we would put in there? 10, right? So that's it. Now we would have a 4-dimensional matrix, which again is hard to think about because we're 3D creatures, but you can think about a sequence of 3-dimensional objects. And it's all stored in one data structure, right? Just one matrix which stores this, right? If someone holds still for 10 frames, so what? You can still store that in one matrix. Again, those of you that go out and code in the real world, these kinds of things are going to be really useful, right? You all know about the big data revolution that's upon us. Think about all the real-time data that's being collected by these kinds of devices. How do you store it? How do you manipulate it? How do you apply machine learning to it so it knows whether you're shaking your phone or gesturing J? NumPy underlies a lot of the stuff that's being built today. Okay, so get familiar with NumPy. Okay, I think that's it about deliverable 3. Again, it's long. There's a lot to learn. Get started as soon as you can. Okay, so back to lecture. As I mentioned, we're going to now start to talk about the design process. We're going to talk about design in general, and then we're going to gradually narrow in on design principles that are specific to HCI. So again, we've got two red boxes here, and these are just going to outline how lecture 4 is going to go. We're going to look at the design process in a lot of different domains, and we're going to start with very subjective domains like fine art, architecture, literature, and move from these more subjective disciplines where you're creating or designing something gradually into increasingly objective or technical domains like engineering, software engineering, and finally HCI. So as you figured out by now, HCI again has sort of a foot in both camps, the subjective and the objective, right? It's not enough to just get your code to run without errors. In many cases, it has to be aesthetic, or it has to be pleasing to the user somehow. So we're going to draw some lessons from these subjective domains about how to create things that people like to look at or interact with when we go about building technical things like software and hardware. Okay, that's where we're going. So we're going to talk about 3 aspects of design. We're going to talk about design philosophy, design process, and design principles, the 3 DPs, as we go. And we'll talk about what those are in a moment. But basically, design is taking some desire or function, something that people use a lot of verbs to describe. I wish I could X, Y, and Z, turning those verbs into a noun. Here's a piece of code or a combined software-hardware system that allows that. So I want you to think about design as a translation. We're going from desired function into a thing, a product. Okay. So when we think about design, we need to think about how are we going to go about making that translation. We spent a lot of time last week talking about who we're designing for, what kinds of activities, context, and so on. We're scoping out exactly, we were last week scoping out what is this desired function? What is it that people want to do, and do they have ideas about how they want to do it? Once we think about that, then we can start to think about, well, how are we going to take all of that stuff about P and A and C and turn it into T? Last week we were just kind of doing it anecdotally, very unstructured brainstorming session and so on, which is fine. But how do we then boil that down into a principled process? We might be able to sit down and think about different ways of doing that. One process might be, great, we've talked to all our users, we take some requirements, forget about the users, go and make our system, debug it, make sure everything works, and finally, when it's all ready, show it back to the users. That's one design process. The other one might be, okay, we take some aspect of this desired need, make a prototype, show you the prototype, get some more intuition about what you want, go back, change the prototype, and so on. Those are 2 different processes. As you can imagine, given those examples, my design philosophy, or the design philosophy in HCI, is that the latter process is more desirable than the former. So design philosophy is a discussion about which kinds of design processes are appropriate for the domain. Okay. So again, we're now going to start looking at design in different domains, starting from the very subjective and walking towards the more objective. So let's start with a domain that is exceedingly subjective, fine art. What are some of the design principles that are maximized or applied in the creation of fine art? So we just talked about design philosophy, we just talked about design principle, now we're talking about, we just talked about design process, now we're talking about the principles of design. What are the sorts of things that are being recognized or maximized or minimized in this process, which in this case is creating fine art? Symmetry is important, right? In some works of art, not all, symmetry is was obviously in the mind of the artist. What else? Color matters. What else? Perspective matters, right? So perspective is pretty important. Sometimes a work of art is made to support your intuitions about perspective. If you're trying to create a work of art that projects 3 dimensions, you usually want to conform to the principles of the human visual system, right? Often, works of art are made on purpose to frustrate our expectations about perspective, right? So M.C. Escher's work is a famous example. So in fine art, we already see that the artist or the designer, if you like, is thinking about sort of what's going on in the observer's mind when they observe, in this case, a work of art, and are they working to support the predictions and intuitions and expectations that the human brain has when it looks at something, or is it trying to frustrate those expectations? Right? That's something that's also important to an HCI designer. Okay, so again, we could enumerate a whole bunch of these aspects or design principles, and you can all probably think of examples from the history of art where those design principles were maximized or minimized or intentionally frustrated. I picked the last one there, maximize ornamentation. Sometimes to create something that's beautiful, you want to try and ornament it as much as possible. Now when we switch from pure aesthetic design to visual design, we're getting slightly more into the technical objective side. And there's a design principle that applies to visual design that we've already mentioned. That's the opposite of maximizing ornamentation. What is it? The idea is to minimize ornamentation, but I used a different phrase for it a couple weeks back. The use of ink, yes, and using ink to do what?
It's about using the least amount of ink to portray the personality.
That's it, right? So we'll come back to this again. In visual design, if you're trying to communicate information rather than just a beautiful work of art, how can you communicate the most information without overwhelming the observer, right? You can all probably think of examples of figures or charts or animations on the web that you've seen where you're completely lost, right? What are they trying to communicate? I like to use the Gapminder examples because I think it's fantastic. If you think about every single colored pixel here, most of them are doing some informational work for you, right? They're communicating some information. There's a minimum of text, there's a little bit, but most of it is pretty clear, right? There's a lot that you can learn about the relative health and wealth of nation states from a single snapshot of Gapminder. You can also choose to ignore a lot of the information that's there and focus on the information that you're interested in. Okay, I wanted to show you an example now. So obviously less is more is a pretty obvious one for a lot of visual design. This is a great video showing how this applies just to spreadsheets. So you go about creating a spreadsheet, you're usually doing it because you either want to compute something of your own or present a large amount of information to an observer. How do you design even just a simple spreadsheet following this principle of maximize the data to ink ratio, or less is more? So this is about a 58-second clip. At the beginning, you're going to see a raw spreadsheet, and then they're going to incrementally remove ink without removing data. The content of this spreadsheet is maybe not so relevant for this class. Okay, So as you develop your ASL educational game, you're going to start to draw more stuff to the screen. At the moment, you're just drawing a 3D wireframe. This week, we're adding in color. You're going to start to add in points and scores and other users and progress over time. You're going to be adding a lot more information to the screen. As you do so, this video is a great reminder to look at what you're developing. You're entering into the enterprise of visual design. As you're sketching out what to show, can you remove some of that information? So in deliverable 3, we're not putting in any text about recording. There's just this intuition that you can turn recording on and off, and it's communicated just through a change of color. So can you communicate to your learner, your ASL learner or your student, what's going on with a minimum of distraction, right? Most of the time they're going to be looking at their wireframe hand on the screen and trying to figure out what's going on. They're going to be paying relatively little attention to all the other visual clutter around it. So we want to try and think carefully about less is more in this case. Okay, so even designing a simple spreadsheet or a visual interface, very important design principle. Okay, let's keep marching from the subjective toward the objective. Architecture is an interesting example because, like HCI, it needs to balance the subjective with the objective, right? Any architect can build a block that is functional, but not every architect can create a building or a space that people prefer to spend time in. However, you're not completely free, like you are in fine art or literature, to create any arbitrary object, right? Now, in architecture, we start to introduce constraints. There's only certain things that you can and can't do. What's the particular building on the left here? Anybody been to Italy? Rome? Vatican City?
St. Peter's.
St. Peter's, that's right. So St. Peter's Cathedral, according to many people, a very beautiful building. How about the building on the right? That's a picture of the outside and a picture of the inside of this building. Much closer to us than St. Peter's.
It's in Cambridge, right?
It's in Cambridge, Mass, yes. It's an MIT building. So this is the Status Center. This is the home of the Artificial Intelligence Center at MIT, designed by Frank Gehry, who's very famous for his hatred of right angles. You can see the outside has this very curvaceous form to it. But inside the building, a lot of right angles. Why? Function, right? Constraints. Most people would prefer to walk on a ground that's perfectly flat. Most people prefer to look out of a window that's in a wall that's perfectly flat, more or less, right? So you can see in the Stata building, there are these concessions to constraints or preferences of people, right? Again, just an object lesson for HCI design. We need to make something that works, that allows people to do whatever they want to do, but we can try and introduce them aesthetics as long as they don't contravene these constraints that exist, right? And what are the constraints? So in a building, it's pretty straightforward when you start to think about it. In a piece of software, it's maybe not so obvious. Okay. Let's keep marching now further to the objective. So let's talk about engineering in general now. In engineering, it's very obvious that someone or some group of people are identifying some need. We're taking that need and translating it into, in a lot of disciplines in engineering, a physical object. So let's take this very complex physical object over here on the right-hand side. Here's a particular design principle, which, again, depending on your design philosophy, you may or may not agree with. Design principle is to try and separate different functions within the same object. We've already seen this design principle a few times already, right? Modularity. When you make your deliverable object-oriented this coming week, you're trying to make your system more modular. It's pretty obvious, right? If you're designing a car, it makes sense to identify different parts, and each physical part, represents or supports a separate function. So engine takes fuel or energy and turns it into motion. Wheels help with making sure that transport is relatively smooth as you move. It would be strange to think of a car that has a different kind of modularity where this system helps with smooth transport and motion generation, and this part does too. Right? Your body is very modular. Different organs do different things. One of the nice things about modularizing the different functions, thinking about all the different functions that your physical object must provide, you can then try and take those functional requirements. So here for our complex object over here, one functional requirement is that it should open cans. A second functional requirement is that it opens bottles. You can then take those two desired functions and turn them into two different parts, in this case, that are physically welded onto the same object, right? So if the function is that it should open cans, a design parameter or a requirement, if you like, is, all right, let's give it a sharp point for puncturing the top of a can, right? We're breaking up all of the things that our system could do into separate functions and then trying to think about different parts of the system that support each of those functions. It's a particular kind of design process which, depending on your design philosophy, you may or may not agree with. Anyways, it will take a function or set of functions, turn that into an artifact which might then be sold as a product. Okay. Getting closer to HCI, now we move into software design, so we can forget about physical objects for the moment. So now that we're talking about software design, unlike engineering or architecture, we may not really be beholden to physical constraints, but there definitely are constraints that apply when we're thinking about designing software. What are some constraints that we would be foolhardy to violate? What about screen space?
Well, all you get is this thing in front of someone.
Okay.
Instead of a physical object, they can put it down there.
Okay. So we have a screen is a good example, right? Whatever the current maximum resolution is, that's all you have, right? If you want to create a Numpy matrix, which is going to store some visualization, that Numpy matrix doesn't make sense for it to have a resolution higher than maximum resolution of whatever screen your software might be displayed upon. I guess it kind of is a physical constraint. But
it's still kind of physical constraint.
Yep.
Memory.
Memory, exactly, right? How much storage do you have? Are there speed constraints, right? Is this safety critical software? Must it run within a certain time period? Is this real time, right? You could violate the real-time feedback loop that you've established, hopefully established with your Leap Motion device, but when you start to violate it and the wireframe hand is moving half a second later than the actual hand, things become very confusing very quickly. You can violate it, but it's not going to give you a very usable product. Okay, what are some design principles that can apply to good coding? One of my favorites is iterate fast and tightly. So as you're coding, you should code and compile if you need to compile, execute and debug as quickly as possible. When I went to grad school, I had a fellow student, a friend who was taking the course along with me. He spent 8 months writing code without compiling it, but he told me it was okay because he'd left the ninth month to debug and get everything working. Unfortunately, my friend didn't pass the course, right? Iterate tightly and often. I think with that anecdote, we'll stop for today. You have a quiz due tonight. Deliverable 2 is due tonight, and make sure to get started on deliverable 3. Thank you.